Good day, everyone. This is the second video lecture on the topic analysis and calculus, and today we are going to investigate more into sequences. And yes, we are going to finally start the first topic that you'll ever take in your calculus class, which is limits. Now first, what is a limit? We start with thinking of sequences, alright? So we start things with sequences, and we know, let's say, if we have a graph, let's say this is a graph of a sequence with index n, and then we know our sequence is an, let's say. Then probably our sequence goes like this. Probably it starts up here, and then there, and then probably after some period of time, it seems to oh, it's starting to get close to this value here. Sorry for my bad drawing, bear with me. This is no good. I probably have to go to attend drawing class. But anyways, it seems to have, it seems like as n grows larger, our sequence is kind of getting very close to some value. Let's call this a. It's kind of getting to a value a. Very close, right? There's still some kind of error going on over there, right? It's not exactly on the line, but it's very close. Now this is called a limit. Well, we're taking n going to infinity and then see what the sequence approaches. It's trying to get very close to a as the sequence goes, as we take the index n to be a very large number, right? Then how do we describe this kind of relationship between the sequence and number a? By limits. Alright, of course, apparently by limits, but how can we strictly define it? So first thing, before we start defining it, I'll tell you about the notation stuff. Since we are now taking an as our sequence here, of course we're going to have an in our notation, right? And then we say it's approaching a, but under the circumstance that we're taking n as a very large number. As n grows larger and larger, the sequence becomes closer and closer to a. So that's something we call limits, and we write that as lim, the first three alphabets, first three characters of the word limit. So we write limit. We're limiting n as it grows very large. Once we take this limit, we know as n grows very large, an is going to be closer and closer to the value a. So we say the limit is a. That's how we write it. But then how are we going to strictly demonstrate that this really is the limit? The limit is really going to a without, probably some term suddenly popping up over here. Right? How can we strictly demonstrate this? Then we have to come up to the definition. So first thing first, if say I'm taking away the first term in the sequence and I form a new sequence, I take away this first term, does it change the convergence of the sequence overall? No, right? What if I take away the second term as well? It still does not change, because it's still converging to this. It's still approaching, or should I say it still gets very close and closer and closer and closer to this value a, right? It does not matter if I keep the first two terms, or first three, first four, or whatsoever, right? That means what? That means if I can find such a number, n. If I can find such a number n, capital N, okay, let's say if I can find such a number n, positive of course, we're doing with a sequence, so we don't want some negative indices, right? If I can find such a capital N, acting as our index, such that when we dump all the terms, we dump the first n terms. Let's just let me rewrite this. If I can dump the first capital N terms, the rest is going to be what? The rest is going to be very close to A. Then I can say the limit is A. The sequence is approaching A, right? Then how do we demonstrate that the rest of the term is very close to A? Now let's think. Very close. What do we mean by very close? Very close means the distance is very small, right? The distance between two things are very small, right? So how do we describe distance between two things, between two numbers on a number line? Absolute values and of the difference, right? So we take the absolute value of the difference from an and a. And then we want this to be very small, right? A very small distance between the two numbers. How do we say it's very small? It's very small when, let's say, if I say its distance going to be 0.001. Since it's very small, I can say the distance is even smaller than this number, right? Is it going to be 0.000000001? No, it's going to be smaller than this. That means what? No matter what positive number you're going to give me, the distance is always going to be smaller than this. But not 0. It's going to be smaller than the number you give, but it's not 0. That means what? No matter what positive number you're going to give me, the distance is always smaller than the smaller than the number you give me. All right? This is the formal definition of a limit of a sequence. Let's review. No matter what distance you give, error or deviation, right? It's not the terms in the sequence may not be exactly on the line. See, there's probably some kind of little deviation. It's not really exactly on the line, but it's very close to the line. So there's some kind of error term there, right? It's got deviation over there. How it, the term that describes the distance from the term to the value a, right? So, like probably for this term, the deviation would be this, right? This distance. It's this distance. Let's say this is epsilon 1. Then we say this term is a3. a3 is of a distance epsilon 1 from a, from the limit a, right? Now, no matter what deviation, what error you give me, I can always find some finite number such that if I dump that number of terms, if I dump the first n terms, the first finite numbers, I can always find this finite number, right? If I dump the first n terms, finite number of terms, if I dump them, the rest of the sequence is going to always have a distance from a less than the deviation you give. All right, again, no matter what deviation you give, I can always tell you how many terms to dump starting from a1, starting from the first term, so that the rest of the terms have a distance from a less than the deviation you tell me. This is the formal definition of a limit. But then it starts to get difficult sometimes, because what if, say, we know the general term of a and it's really, really complicated? Then is there any kind of way that we can know that this sequence has a limit without having to evaluate the limit? Right? Because when the general term of an, the sequence, gets very, very complicated, what do we want? We do not want to evaluate the limit because it's complicated. It's gonna annoy us a lot. So is there any kind of possible means for us to determine whether the sequence is going to have a limit by only taking a look at the general term itself? Yes, there is. The answer is positive. Now, Cauchy, there's someone called Cauchy. I'm not sure about the pronunciation, but there's this guy called Cauchy, Cauchy. It's gonna spell Cauchy. There's this mathematician called Cauchy, probably pronounced like this, but I ain't really sure about that. Should be. There's this guy called Cauchy, and then he says that for a sequence to have a limit, now let me just do some terminology stuff. Have a limit exists means it's converging. It converges, all right? A sequence converges means there is such a number a such that we have this limit. All right? We can find a number a such that it's the limit. That means it converges, all right? So Cauchy says that if we have a sequence that converges, then when we dump the first n terms, the rest of the term is going to be very, very, very close to each other. No matter how you pick the index, the rest of the terms, any two from the rest of the term, are going to be very close to each other for the limit to exist. And this is called the Cauchy convergent principle. Cauchy convergence principle. Convergence. Ouch. Principle. Right, this is the Cauchy convergence principle. It says, a little bit different from before now, no matter what deviation you give me, I can always tell you how many terms starting from the first to be dumped so that for any two terms from the rest, n1 and n2, both larger than n, I can always assure you that the two terms are going to be very close to each other. That means the distance between between any two terms from the rest is going to be smaller than the deviation that you give me. Alright? This is the Cauchy convergence principle, and for any sequence that satisfies this principle, we're going to call them Cauchy sequences. Now that's one other way to find out whether a sequence is going to converge by looking at its general term only. But then what if the Cauchy convergence principle is not enough? Probably some kind of sequence involving say -1 to the nth. Then how do you know how are you gonna do this, right? If I say an, the general term is -1 to the n times some kind of function of n, let's say sine n, how are you gonna determine that a of n1 minus a of n2, right? It's gonna be hard. So how can we deal with such cases? Now, there's something to notice. From before, I said when we take away the first term, it's not going to affect the overall convergence or divergence of the entire sequence, right? If it's going to converge, the rest of the term will still converge. If it's going to diverge, meaning this a does not exist, the rest of the term is not going to be very close to a number, then after I remove the first term, it's still gonna be like diverging, right? Same for the second term. If I dump the second term, still the convergence or divergence is still not going to be affected. That means what? Now there's something that we call a subsequence. Like, not the thing you're gonna suffer from when you do something bad, not the not that kind of subsequence. But that means a sequence that is inside another sequence. For example, let's say we have a sequence an, which is exactly equal to n. And then say we have another sequence bn, which is the odd numbers, 2n minus 1. Now this is apparently 1, 2, 3, 4, 5, right? Sorry, should be a comma. Right? And so on and so on, and then bn is going to be what? It's going to be 1, 3, 5, 7, 9, and so on, right? Now apparently we can see if this bn is treated as a set, we can apparently know that bn is a subset of an, right? And more obviously, bn is a proper subset of an, but that doesn't matter, proper or not. We can always say from this that bn is a subsequence of an. Again, bn is a subsequence. Is a subsequence of an. And why am I trying to bring up this subsequence thing? When we're not doing something bad, we're not supposed to be punished with some kind of subsequence. The thing is, for a limit to exist, all of its subsequences has to have limits, and they all have to be equal. That means what? Let's say we have a sequence, say it's -1 to the n. Let's say an, this is a sequence, -1 to the n. Now if you draw the graph of this an, the first term is going to be what? It's going to be 1. And then second term, first term is going to be -1. Second term going to be 1. Third term is -1. And then 1, and then -1, 1, -1, 1, -1, +1, -1, +1, and so on, right? If, let's say I'm taking bn as the odd number terms of this an, that means I'm going to take a 2n minus 1, right? Odd number terms. This means what? bn is going to be -1. So if I'm taking the limit of this bn, what is it going to be? The limit of bn is definitely going to be -1, because every single term is -1. We don't need to prove any convergence or divergence. It's going to be -1 anyways, right? If now I take cn is going to be the even number terms, a to n. It's going to be 1, right? So same thing, the limit of cn is going to be 1, because every single term is cn. We don't really have a deviation. The deviation is always 0 no matter what, right? So we have a limit for bn, one of the subsequences of an, as well as cn, but they are not equal, right? They are not equal, but they have a limit. Then what? How do I know if the limit of an is going to exist? Now what does it mean when an has a limit? When an converges? It's getting closer and closer to a value, right? If an is getting closer and closer to a value, should bn getting closer and closer to that value? And cn as well, right? Because the subsequence is, well, from some kind of way, from another different perspective, a subsequence can be thought of as choosing the terms from the original sequence. Right? Cn is formed by choosing the even number terms from the original sequence an. What about bn? Bn would be choosing the odd number terms from the original sequence, right? So that means if we have a limit, if an is converging, if an converges, that means what? Bn should also converge as well, because Bn is chosen from an. Cn converges as well, because Cn still is chosen from an. What values should they converge to? Since both of them are chosen from an, then of course both of them should converge to the limit of an. Both of them. But now bn and cn is what? They both converge, but they converge to something different, right? They converge to something different. That means what? That means, does an converge? No. So we end up with the conclusion, for a sequence to converge, an converges if a sequence converges, ouch, then let me write it this way. If a sequence converges, then all subsequences, not because it's doing something bad, not because it's nasty, all subsequences should converge to the same, converge to the same value. Sorry for the bad handwriting. So that's another way for us to determine whether a sequence converges. So we've talked about what for now? The definition of a limit, right? No matter what deviation you give, I can always tell you how many times to dump starting from the first, so that everything from the rest is going to deviate no more than the deviation you tell me from the limit a. And then when we do not know the limit a, we can use Cauchy convergence principle to know if two terms, after dumping finite number of terms from the first, if any two terms from the rest is very, very close to each other, then we say the sequence is a Cauchy sequence as well as it converges. And then we also know we can determine whether all of its subsequences converge to the same value. Now this one, the all subsequences converge to the same value test thing, is very good for testing if a sequence diverges. Right? It's hard to test for all subsequences being convergent to the same value, but it is not to test if two subsequences converge to different values. So this one is very good, is a very good use when we want to test that a sequence diverges, especially in our case, an is equal to -1 raised to the nth power. When we want to prove something is divergent, this testing for two subsequences converging to different values, or one of the subsequences does not even have a limit, then we can directly know that the original sequence is going to diverge, does not have a limit. Now that we know that, now that we know some test to determine whether a sequence converges, can we know something about convergent sequences? Like, is there any properties about these converging sequences that we might want to pay attention to? Of course there is. It's not there for no reason. There must be something that we have to pay some kind of attention to. So, properties of convergent sequences. First thing is that, not really properties now, probably some more conditions for sequences to exist, for limit of sequence to exist. Now, if I'm thinking that, the tests above are too difficult for me, I don't really want to use them at the moment or for now, then what can I do? Are there any other methods? Are there any other means for me to know whether a sequence has a limit? We can make use of the fact that we learned from last time that sequences can be treated as sets, and sets has what? Supremum and infimum. Right? So the first theorem we're gonna cover today is that if a sequence has a bound, if a sequence is bounded, then it's going to have a limit. Now the restriction is that if a sequence an is monotonically, sorry for the ugly A there, if a sequence is monotonically increasing, and is bounded above. What does it mean by bounded above? Means supremum exists. Bounded above means there is an upper bound. So from last time we know, if an upper bound exists, we must have a supremum. So I'm going to rewrite here. And supremum of an exists, then, now interestingly, I'm not just gonna say that the limit of an exists, but instead, the limit as n approaches infinity of the sequence an is exactly going to equal the supremum of an. Now this is something quite interesting, right? So why is it so? Now if I'm changing this to decreasing, I'm changing this to monotonically decreasing, and that its infimum exists, then the limit is going to equal infimum. But for now, I'm just gonna prove the increasing case. The infimum case can be, as all math book does, left to the readers as an exercise. So I'm just gonna prove the supremum case, because the infimum case is very similar. Now first, from the fact that we know supremum of an exists, we know what? We know for all epsilon larger than 0, there will be an n larger than 0 such that the supremum of an minus this epsilon would be smaller than a of capital N. That means what? The supremum largest upper bound, meaning that if it decreases a little bit more, it's gonna have some terms being larger than the number. That means it can't get smaller. If it gets smaller to some other number b, then this b is going to be smaller than some of the terms in the sequence. Then it's not an upper bound anymore. But now since we're gonna have this, then that means what? That means what? Under this situation, we can, like, from the definition here, for all n larger than n, right? We have this first part being exactly the same, so we can just add something else. For all n larger than this capital N, we can conclude what? We can conclude that the supremum of an, of the sequence an, minus epsilon smaller than an, with a of capital N, which is exactly the same as the thing above. Now, an is a monotonically increasing sequence. What does that mean? When the index gets larger, the term in the sequence also gets larger, right? So this is going to be smaller than an. Right? So we also know that the supremum is always going to be what? Larger than or equal to every single term. So we can say we have an, any small n there is going to be smaller than or equal to the supremum of an. But then that means if I add a little bit to the supremum, it's going to be larger than supremum, right? If I add a little bit, it's going to be larger than the supremum. So now let's take what? Let's take this, and this out from the inequality. We get what? We get supremum of an minus epsilon is smaller than an smaller than supremum of an plus epsilon. That means what? If we know absolute value, that means this thing means an minus supremum of an is going to be smaller than epsilon. The distance between an and supremum of an is going to be smaller than epsilon. What does that mean? From the definition of a limit, no matter what you give, I can always tell you how many terms to dump from the first term, so that everything from the rest is smaller than the deviation you give me from the limit, right? That means what? This thing here is exactly our limit. That means limit as n approaches infinity of an is going to be what? Is going to be supremum of an. There we've proven the theorem. That means whenever we're going to see a monotonically increasing sequence, and we can also find its supremum, then the limit of the sequence is going to be exactly equal to the supremum. Interesting, right? Now the monotonically decreasing case will be left for you as an exercise. So I'm not going to do it here. And it's just going to be very similar to this proof, so no worries. If you can understand the proof, from the beginning all over to the final result, then you should be fine with proving the monotonically decreasing and the existence of Feynman case. Now that is a much easier way of determining the convergence or divergence of a sequence, right? But it's just that we are not restricting ourselves. We're not allowing ourselves to generalizing to like any kind of sequence. It requires monotonicity, right? But still, it's useful. So now there's something else that we probably want to like pay attention to. If you've taken your calculus lessons already, then you probably might have heard of the number e. Or if you have been watching, Facebook memes, there's many cases where they say pi is like approximately equal to 3, and then there's some other number e that they say is equal to 3, and so yeah, a lot of mess going up, right? What exactly is that e thing? Now the introduction of the quantity e may differ between textbooks, but I'm going to stick with one of them about compound interests. That means when you're gonna save money into the bank and then the bank gives you interest, so that the money you're depositing is going to be increasing every year or every compounding frequency. For example, if I'm paying $1, I don't know, in any kind of units, say, in any unit, if you're in Hong Kong, you do Hong Kong dollar. If you're in United States, you get USD. If you're doing like, if you're in the European countries, probably you're doing euros. If you're doing, what else? Just use the unit in your own country for the sake of it, for the sake of better comprehension. So, say we have $1. $1. Our principal P is $1. I'm just gonna use this symbol for the moment, alright? Don't kill me. Okay, I'll just write principal equals what? The rate is R. Percent per annum. Meaning that every year the interest rate is R%. And then compounding frequency, I'm gonna say it's n times a year. N times a year. The rate, called the interest rate. If you went into a bank, interest rate. Now, what is the amount of money that I'm going to get after a period of time, after t years, say? The amount A of t is going to be what? After the first t, I'm going to get 1 plus R% over n raised to the power of nt. Raised to the power of n. Now, there's someone who says, is there a kind of way, let's just write AET here, and that means A1 is equal to 1 plus R% over n to the n power, right? Now, there's someone who says, excuse me, P as well, principal, And then if you started with $1, then the p is equal to 1. I'm just gonna write it this way. Why am I saying p equals 1 anyways? So let's say we're dealing with this A1. Then someone is gonna say, how can I maximize my profit? If I am to save your money into a bank, or if I have to like lend money to someone else, and then you're dealing with this compound interest stuff. You want the guy who borrowed money from you to like give you back more. Then how can I maximize my own benefits, right? Being a little bit greedy here. How can I maximize my profit? How can I maximize the money I get back? Of course, the first very obvious thing is that I maximize the rate, right? I maximize the rate. So that means I'm going to have A equals P times 1 plus, the rate at most is 100% assumed. So it's going to be 1 over n to the n. That means, what else? What else can I do? I can increase the compounding frequency, right? The more that I do with n, the more it's going to increase. Right? The more I increase n, the more a is going to increase. Why? Let's see. We will prove here that this function is indeed increasing. So first, let us move this p over to the left, because this p is constant anyways. It's not gonna be 0, then a is gonna be 0, then there's nothing to worry about here. We're not gonna maximize anything, right? You started with 0 anyways. So move p over, we get a sequence an equals 1 plus 1 over n to the nth power. Now we have the sequence, and we are now to prove that this is increasing. This is monotonically increasing. What do we have to do? What does monotonically increasing mean? If a sequence is monotonically increasing, then for all positive k, an plus k must be larger than an. Right? The larger the index, the larger the term. Alright, the larger the index, the larger the term. Might not really be a strict inequality. You can change that to larger than or equal to. It's still monotonically increasing. Not strictly increasing. Right? So we're gonna do something that is a little bit complicated here, so bear with me. Now, n is a positive integer, right? We're dealing with a sequence, so we can use binomial theorem. Binomial theorem says, if you forgot, binomial theorem says a plus b to the n is equal to the summation of r going from 0 to n of NCR combination n combination r times a to the n minus r times b to the r. Now our first thing here is 1. 1 raised to anything is just 1, so we're going to ignore the 1 here. It means this is going to be leaving us with what? With 1 over n to the r times, don't forget we have the time, we have to multiply that by NCR. Right? So let's expand this. When r is equal to 0, what do we have? NC0 is gonna be 1. 1 over n to the 0, it's still gonna be 1, right? And then plus, when r is equal to 1, we get n, and then this is 1 over n. And then n times n minus 1 over 2, that's nc2, times 1 over n squared, and so on. Right? And so on. And I'll also write the sometimes in the middle, say the kth term is going to be n times n minus 1 times all the way up to n minus k plus 1. Divided by k factorial times 1 over n to the k. And then finally, our last term is going to be NCN is still going to be 1, right? NCN is 1, and then finally we have 1 over n to the nth. Now, if I do some distributions, this is 1, this is 1, so these two add up to 2. If I distribute this, now I'm gonna call this exploding the parentheses, alright? This thing is gonna become n squared minus n. This is what I call exploding the parentheses from now on. Alright, if I explode this parentheses and then I divide this by n squared as well, I get what? I get 1/2 1 minus 1 over n. And then, similarly, I'm going to take out this k factorial for the kth term. For n to the k, the rest of the stuff, it's going to become 1 minus 1 over n, 1 minus 2 over n, 1 minus 3 over n, and all the way up to what? Up to 1 minus k plus 1. Excuse me, k minus 1 over n. Right, and so similarly, we're going to get, the last term is going to be 1 over n factorial, just, generalizing up to the nth term. 1 over n factorial times 1 plus 1 over n, 1 plus 2 over n, and so on, all the way up to, oh sorry, not a plus, it's a minus, excuse me, all the way up to 1 minus n minus 1 over n. Right? This should be good, right? Because if we do the third term, now if you don't believe me, if I do the third term is going to be n times n minus 1 times n minus 2 divided by 3 factorial times 1 over n to the cubed, right? So if I take out this 1 over 3 factorial, I'm going to get n minus 1, n minus 2. If I explode this parentheses, it's going to get n squared minus 3n plus 2. Multiply that by n, we get n cubed minus 3n squared plus 2n. Dividing that by n cubed, we get what? We get 1 over 3 factorial, 1 minus, let me take out the minus there. I'm going to get, oh wait, we don't need to explode the parentheses there. We're gonna get what? N divided by n minus 1 divided by n, and n minus 2 divided by n, right? So this is gonna be 1, so I'm just gonna ignore this here. And then this is explode parentheses for the second term. It's gonna be 1 minus 1 over n, and 1 minus 2 over n. Right, so the same thing happens for the kth term. This term is actually just equal to n minus what? K minus 1. So distributing these n's over to the numerator, you get 1 minus 1 over n, 1 minus 2 over n, all the way to, what is this? 1 minus k minus 1 over n. Right, so the kth term is going to be of general term this form. That's why the nth term is gonna be this form. Alright, so now we have this. What are we gonna do with this messy stuff? This is so messy. Right, let me rewrite this so that it doesn't look so ugly. The letter N does not look so ugly now. Ouch. There. So now what do we do with this pile of mess? It's so messy now. What should I do? Now this, we can, from here, we can actually do something which is tricky, which is to increase denominator by 1 in every single parentheses. That means we're going to get 2 plus 1 over 2, 1 minus, increase that by 1. I'm not gonna tell you why at the moment, but let me just finish this first. Oops, and plus 1 plus ouch. Excuse me, n plus 1, 1 minus 2 over n plus 1, all the way to 1 minus n minus 1 divided by n plus 1. Now, the reason I'm doing this will be explained a little bit later, but now we know every single denominator is increased. That means what? When the denominator is increased, then the value of the fraction, let's compare 1 over n and 1 over n plus 1. Which one is going to be larger? 1 over n is larger, right? So 1 minus 1 over n is going to be what? Larger than or smaller than 1 over 1 plus 1 minus 1 over n plus 1. Which one is going to be larger? This is larger than this. That means we're subtracting more from 1 in 1 minus 1 over n. This thing is subtracting more from 1. This thing is subtracting less from 1. Means what? Which one is going to be larger? This one is going to be larger, right? So for every single time I do this operation, making this change larger, right? I'm changing every denominator. I'm increasing every single denominator so that I'm subtracting less from 1 in every single factor. Means I'm increasing the overall value. But look, an is equal to this thing. If I'm changing n to n plus 1, what does that do? I'm actually getting n plus 1, right? If I'm changing n's to n plus 1s, I'm actually getting what? I'm actually getting n plus 1. But now, wait, no. Why have I forgotten this? I have to change this as well. Right? If you compare the terms from all the way up to 1 over n factorial, the terms are increased except this 2. And then I also have to add another term, so of course it's going to be larger, right? That means what? As the term gets larger, as the index gets larger, the term gets larger. An is smaller than an plus 1, means an plus 1, the larger index, the term with larger index, is larger than an, the term with smaller index. Right? That means an is increasing. Now what's good about increasing sequences again? means if we can somehow find the supremum, then the limit is gonna be the supremum, right? Or should I say, if we can find an upper bound, then the limit exists, right? We don't really have to know that it's gonna be we don't really have to like evaluate the supremum yet, because when we have an upper bound, we know the supremum exists, so the limit exists, right? So let's see if we can find an upper bound. See if we can find an upper bound. Now, from here, I'm subtracting something from 1 in every single factor, right? So if I take away these factors, I will not have to multiply something less than 1. Because multiplying by something less than, a little bit less than 1 means that I'm decreasing the overall values of each term. Now if I take away these factors, I'm gonna get what? Something larger, so an smaller than 2, the first term was 2, and then 1 over 2 factorial, 1 over 3 factorial, right? I'm taking away all those factors with 1 minus something, so all the way 1 over k factorial plus, and then all the way up to 1 over n factorial. Now this is still a pile of mess because factorials are very hard to deal with. Now if I take away some terms from the denominator, look, 2 factorial is what? 1 times 2, so I can write 2 plus 1 over 1 times 2. It's not going to change the value. 3 factorial is 3 times 2 times 1. The times 1 can be ignored, does not change the value, so it's 2 times 3. Right? And then 4 factorial is what? Let me write an extra term here. Excuse me, 1 over 4 factorial. What is 4 factorial? 4 factorial is 1, 2, 3, 4, right? Now take away the 1 here, this does not affect the value. Now what happens if I take away the 2 as well? It's going to increase, right? If I take away the 2, that means I'm doubling this term. So the value is going to increase, right? Same thing happening over there. I'm taking k minus 1 times k all the way up to n minus 1 times n. Now this is much better looking because we can do partial fractions. Let's deal with this, a more general case. What is this equal to? You know partial fractions, you know 1 over k minus 1 times k should be broken up into a over k minus 1 plus b over k. Cross multiply, I mean multiply by the denominator here. We get what? We get 1 equals ak plus b k minus 1. That means if two polynomials are equal, then the coefficients must be equal. So the coefficients of k on the left is 0, on the right is a plus b. The constant term is 1 on the left and negative b on the right. That means we get b is negative 1 and a would be 1. So now what we get is that we know this is equal to 2 plus what? The smaller one gets positive 1, right? The smaller one gets positive 1. The larger one gets negative 1. So the smaller one gets positive 1. Ouch. Why is it not good? Smaller one gets positive 1. The larger one gets negative 1. smaller one gets positive 1, larger one gets negative 1, and so on. I'm just gonna skip the case term. Smaller one gets positive 1, larger one gets negative 1. Now this is a telescoping series. Telescoping sum actually. What do I mean by that? Telescoping means you have negative 1/2, positive 1/2, negative 1/3, positive 1/3, and so on. These terms are all gonna cancel up all the way up to here. So we are left with what? We're left with 2 plus 1 over 1 is just 1 over 1 is what? 1 over 1 is 1, and then we are left with this minus 1 over n. So this can be simplified to just 3 minus 1 over n. And we know when we want to find an upper bound, we do not want this n to be disturbing us, so this term is what? 1 over n is a positive number, so 3 minus some positive number is gonna be less than 3. Oh hey, we found an upper bound. 3 is an upper bound of an. That means what? Upper bound exists, so supremum exists. Supremum exists, so limit exists. Right? We don't really have to like prove that that limit exists, or we don't really have to evaluate the limit to know that this limit exists. Now, what exactly is the limit then? We're kind of curious. We're kind of curious to know about the value of the limit of this sequence, right? 1 plus 1 over n divided to all the raised to the n power. This is the limit is denoted as the letter e. All right. So now we know. Let's conclude a little bit, since an not monotonically increasing now. An is strictly increasing. If something is strictly increasing, it must be monotonically increasing. An is strictly increasing. And we know 3 is an upper bound. 3 is an upper bound means supremum of an exists. Supremum of an exists, and an is strictly increasing. Then that means what? That means the limit as n approaches infinity. Why is this so ugly? The limit as n approaches infinity of an exists. Right? This exists, and now we're gonna tell you that this limit is denoted as e, excuse me. This limit is denoted as the letter e, known as the Euler's number, also the natural constant. And its value is approximately 2.718281828. Not a recurring decimal. It's not gonna be 1828 repeating forever, but the value changes after the second time of 1828 appears. 1828, 1828, and then some other numbers. Right? It's not recurring, it's irrational. So there, we've introduced this e here. So next time when we see some kind of limit, and having this kind of form of 1 plus something raised to the something, then we probably want to think of e, alright? It's probably related to e. So, but anyways, I'm going to leave the evaluation of limits for the next lecture. But for this lecture, what we've learned so far is the definition of limits. We've also learned the Cauchy convergence principle, and that a converging sequence must have all of its subsequences converging to the same value. We have also learned the the theorem that says monotonically increasing sequences with an existence of supremum means the existence of limits, and same thing for monotonically decreasing sequences having the existence of infimum also implies the existence of limits. And we also finally we also introduced E, which comes from this interest rate thing. That means when you put into your bank $1 and you expect 100% of interest rate per annum, then the maximum amount that you're gonna get after the first year is $E. Right? So no matter what principal you're gonna get, you're not gonna get triple times. All right? It's not gonna reach 3 times the principal. Right? Now that's all from this lecture, and I hope you enjoyed. See you next time.